Welcome to the class of stochastic processes. The Gamber's ring problem. The Gamber's ring problem is actually an abstraction of many practical problems. And the problem is about answering the following question. What is the probability that starting with I units, the gambler's fortune will reach N before reaching 0? So the gambler's fortune starts with I unit. And there is probability P that for every game, the gambler will earn one more unit. So the gambler's fortune could move from I to I plus 1. And there is probability Q that the gambler's fortune will lose one more unit. So the gambler's fortune will move from I to I minus 1 with probability Q. Now, if we let Xn be the player or the gambler's fortune at time n, then Xn is a Markov chain. Now, we have what follows. First, P00, which means the probability that the gambler's fortune start with 0 unit will reach 0 unit is equal to 1. Similarly, Pnn is equal to 1, 2. Number 2, Pi plus 1 is equal to P, which is equal to 1 minus Pi minus 1. Number 3, there are 3 classes, 0, 1, 2, 3, up to n minus 1, and n. And because the gambler's fortune will eventually reach 0 or n, and the game will be over. So 0 and n are recurrent states. And 1, 2, 3 up to n minus 1 are transient state, meaning they are all temporary. Now we let Pi be the probability that starting with I units, the gambler's fortune will eventually reach n, which is the question we would like to answer in this problem. So Pi can be written as the conditional probability that eventually reach n given we start with I unit, and the first game we earn one more unit, so S1 is equal to I plus 1, times probability that S1 is equal to I plus 1, plus conditional probability that eventually reach n, and we start with I unit. And the first game will lose one more unit, so S1 is equal to I minus 1 times probability that S1 is equal to I minus 1. And because S1 is equal to I plus 1, this is equal to P, and this is equal to Q. And also because X0, X1, X2, all the Xn is a Markov chain. So given X1, we can actually ignore X0. So X1 is equal to I plus 1. Eventually we will reach n. The probability can be written as Pi plus 1. And similarly, this conditional probability can be written as Pi minus 1. Now, Pi can be written as Pi plus QPi, because P plus Q is equal to 1. So that is equal to Pi plus 1 plus QPi minus 1. So if we organize this equation, we get this. Pi plus 1 minus Pi is equal to Q over P times Pi minus 1. Now, if we plug in I, for example, I is equal to 1, so we have P2 minus P1 is equal to Q over P, P1 minus P0. And because P0 is equal to 0, so we have Q over P times P1. And similarly, we can keep going up to Pi. Now, we can sum up these equations for the left-hand side and the right-hand side. So for the left-hand side, we know that P2, P3, P4, all of this can be cancelled out. So we are left with Pi minus P1. And for the right-hand side, this is actually a geometric series. So we have two cases. Number one, if Q over P is not equal to 1, then Pi minus P1 will be equal to P1 times this geometric series. So we get this result. And number two, the second case, if Q over P is equal to 1, then Pi minus P1 is equal to P1 times 1 plus 1 plus 1. And that is P1 times I minus 1. So if we move this P1 to the right hand side, we have Pi is equal to I times P1. Now, if we know P1 here, and then we can plug in T1, and then we know Pi immediately. So, what is P1? But because we know that Pn is equal to 1, right? So we could actually plug in n here. So Pn is equal to P1 times this 1 minus Q over P to the power I divided by 1 minus Q over P. Or the second case, Pn is equal to n times P1. That is equal to 1. So based on this fact, we can solve for P1. So P1 could be either like this, or P1 could be like this. And now we plug in P1 to the previous equations, so we get Pi like this. Now we can do some analysis. So if P is greater than 1/2, then we know that Q over P is not equal to 1. So, and also the denominator, when n goes to infinity, the denominator will go to 1. And so we are left with the numerator, which is 1 minus Q over P to the power of I. On the other hand, if P is less than or equal to 1/2, and we know that this Pi could go to 0, like this. 1D random walk. We first present a definition of so-called closed. A non-empty set C of state is said to be closed if no state inside of C leads to any state outside of C, meaning Pxy is equal to 0. X belongs to C and Y does not belong to C. So Pxy is equal to 0, meaning X cannot go to Y. 1D random walk. 1D random walk is about starting with I unit, and there is P probability that we could earn one more unit, so we move from I to I plus 1. Or we have Q probability that we could lose one more unit, so we will move from I to I minus 1. Now, if we let a random variable xn be x0 plus z1 plus z2 up to zn, and we start from 0, and all the zi are IID of random variable, either 1 or minus 1 with probability p or q. And then we can see this Markov chain is actually irreducible and closed. So that means all states are transient or recurrent. So we just need to check one state. If, for example, if we check the state 0, if state 0 is recurrent, because this Markov chain is closed and irreducible. So if 0 state is recurrent, all states in this Markov chain is recurrent. On the other hand, if 0 state is transient, all other states are transient. So we just need to check F0, which represents the probability that the process will return to 0 given we start from 0, whether or not this is 1 or less than 1. And we have learned that if F0 is equal to 1, meaning eventually starting from 0, the process will return to 0. That means summation P00n is equal to infinity, because this represents the expected number of times that the process will return to 0. And if 0 is the recurrent state, then this quantity must be infinity. On the other hand, if this is a transient state, then we only have finite number of times that the process will return to 0. So this quantity must be less than infinity. So if we want to check this is f0 is 1 or less than 1, we just need to check this quantity, right? So this quantity p00n is, we start from 0, and what is the probability that after n step we return to 0? So that is xn is equal to 0. Now, if we start from 0 and we want to return to 0, that means z1 plus z2 plus zn must be 0. So if we let A represent the number of positive 1 and B represent the number of negative 1, and because z1 plus z2 plus zn must be 0, so A plus B must be n, and A minus B must be 0. So that means we only have one possibility, which is A is equal to n over 2, and B is equal to n over 2. Now we calculate P00n. So that means if n over 2 is even, so n over 2 of n, we have positive 1, and n over 2 of n, we have negative 1 trials. So that means this probability means we have n choose n over 2, p to the power of n over 2, and q to the power of n over 2. So summation p00n is equal to summation of this. And notice that because n choose n over 2 only have positive values when n is even, right? So we can write this as this. So we C2nn, p to the n, q to the n. Basically, we just double this n here. Why we do that? Because n over 2 only have positive values when n is even. So we could just double all of them. So we have summation like this. And we all know that this combination can be written as factorial, like this. And by Stirling's formula, as we will describe later, this factorial divided by factorial can be written like this, times pq to the power of n. And if we organize the equation like this, and further, we can move the 1 over square root of pi outside of summation, because this has nothing to do with n, right? So we can write the equation like this. Okay? So this is Stirling's formula for your reference. Now, we divide the problem into two cases. If P is equal to Q is equal to 1/2, then this quantity that we are interested in will be equal to square root of 1 over square root of pi, summation 1 over square root of n. And this is a P series where P is equal to 1/2. And we know that this is equal to infinity. Why is that? Because we know summation 1 over n is equal to infinity. So we know that summation 1 over square root of n must be infinity too, right? And the second case, if P is not equal to 1/2, and then we know that this is less than infinity. Okay? So this case, that means the zero state is transient. So the conclusion is like, if P is not equal to 1/2, f0 is less than infinity. So all states are transient. On the other hand, if P is equal to Q is equal to 1/2, and then all states are recurrent. 2D random walk. So now we have 2D. So we have xn and yn. So also the r square, meaning 2D, this is still irreducible Markov chain, right? So we want to check if this is transient or recurrent. We just need to check the state of 0. So for every move, you could from 0 to this direction, this means Z1, W1 is equal to 1, 1. Or you can move to here, that is 1, -1, or -1, 1, or -1, -1. So we have 4 possible directions. So Xn, Yn is equal to Z1 plus Z2 up to Zn, and W1 plus W2 up to plus Wn. And we know that all Zi and Wi are IID copies of either +1 or -1 with probability P or Q. So if for this process, if we start from 0 and we want to return to 0, and that means for x-axis we have to return to 0, and for y-axis we have to return to 0. And we have known that for the x-axis we want to return to 0, the probability is actually equivalent or very close to, we could just look at like 1 over square root of n, right? And yn is equal to 0 is equal to 1 over square root of n times 1 over pi. So that is 1 over n pi. And if p and q are both equal to 1/2, we know this is infinity. So that means all states are recurrent. But on the other hand, if this is not equal to, all of them are not equal to 1/2, and we know that this state is actually transient because this quantity is less than infinity. Further, for 3D random walk, now we have 3D, so we have A, B, C, 3 directions. Okay, so if we want to return to 0, from 0 to 0, all of the A, B, C must be 0. So that means the probability would be the summation of C over square root of n and to the power of 3. And that must be less than infinity. So that means regardless of what values of P and Q, this process is always transient. Heating times. Let TA represent minimum n, Xn belongs to A. So in this case, TA represents the heating time. So for example, if this is our process, we start from here, and this is, for example, A. And we start from here and like this. And that is the first time we hit A, right? So in this case, this is called heating time. So that is TA. This is the time that we need, the first time that we hit A. So that is the heating time. We let TA be infinity if the process never hit A. And so TA in word, that means the first positive time the Markov chain is or hits A. We have the following proposition. Pxyn is equal to summation Px, and Ty is equal to n, then Pyy n minus n. What does that mean? That means we start from x, and after n step, we go to y. And this probability can be written as summation that we start from x, and the first time we reach y is equal to n, and we sum over all possible n. And then p, because the first time we hit y is equal to n, but eventually we want to be at y at time n, right? So we are left with n minus n steps. So P, Y, n minus n probability would be like this. Now, we mathematically prove why this is true. Note that the event Sn is equal to y. This event can be decomposed as the first time that we hit y is equal to n, and Sn is equal to y. And we take union of all possible n. Now, Pxyn, so that means Px, and after n step, the process is at state y. So we can decompose that. by the first heating time, right? So that is Ty is equal to M. And we sum over all possible M here. And based on the conditional probability that we know this quantity Px Ty is equal to M, Xn is equal to Y can be written as this. And then what does that mean? So if we look at this, this conditional probability, and that means because the first heating time is M, so that means X0 is X like this. And the first heating time of Y is M, so the first time, so X1 is not equal to Y, X2 is not equal to Y, X3 is not equal to Y, Xn minus 1 is not equal to Y, up to, so the first time, Xn is equal to Y. So that means Ty is equal to M, right? Because that simply means the first time that the process hit Y is at M step. So we can return this conditional probability like this. Pyy M minus M. So that means we start from Y. Okay, because the first time we hit Y is the M step. So Y, and after N minus M step, we are back to Y, right? So P Y Y N minus N. So the probability can be written like this. So, and we complete the proof. Proposition. A state, we first present a definition. A state A of a Markov chain is called an absorbing state if PAAM is equal to 1 for any M between 1 and M. So that means, so we have proposition here. So if A is an absorbing state, then PXAM is equal to PXTA less than or equal to M. And why is that? Well, this is actually very straightforward because PXAN, that means we start from X. And then the first time we hit A is M step. And then we are left with N minus M step, right? And we want to start from A and back to A after N minus M step. And we can take summation for all possible M. Now, this PAAN minus M, this, because A is an absorbing state. So regardless of how many steps, PAAN minus M must be 1. So we are left with PXTA is equal to M. And if we take summation here, we simply mean the probability that we start from state X and TA less than or equal to